This is Professor Geisler at Gustavus River College, and this is your short video lecture for Section 7.4 IP version 6 for CISN 301 using the TestOut Client Pro 8.0 curriculum. And we're not going to spend a whole lot of time on IPv6. It is being used, but a lot of it that we would have to worry about in the IPv4 address space is taken care of itself, really, so we don't need to worry a whole lot. But we are going to take a look at how to configure a DHCP6 server, which will, because the address space is slightly different, will need to work somewhat differently. And we'll also take a look at how to configure an IP version 4 address. Now, here's some terminology related to IPv6. So we'll talk about the prefix and interface IDs. We'll take a look at tunneling, but that is a temporary thing to connect between IP version 4 and 6. And we'll take a look at the various types of addresses that exist within IPv6, differently so than they do within IPv4. We've heard of multicast, we've heard of loopback, but let's talk about that in a little bit of detail. So first, since an IPv6 address has 128 bits, the first half, the first 64 bits, is what we call the prefix ID. Okay, and that is where we can subnet, if you will. So it gives us a lot of space to do that within these first 64 bits. And we can do so by geographic region, by ISP, by network, etc. The interface ID then, that is your host address, if you will. So the unique identifier for each device, similar to a MAC address, okay? And that is within that subnet as we defined in the prefix. Now, we do have some institutions already completely on IPv6, and of course, many others still using IPv4. So we need to be able to run both. So we can actually use a tool or a technology called tunneling that would allow hosts that are using IPv6 addresses to communicate over the existing infrastructure. More about that later. A regular address, one host to send and receive data, as we would call it, just a regular IP address, is known as a unicast address. Okay, so it goes to the host that has that address. A multicast address goes to a dynamic group of hosts that would be like a class D address in IPv4. Okay, and an anycast address goes to more than one interface, and usually again belongs to different hosts. So how is that different from a multicast address? The context of dynamic is a factor here. More about that later as well. And then loopback addresses, just like the 127.0.0.1 in IPv4, we can use a loopback address to make sure that our IP stack is properly running. And again, that'll help us with troubleshooting. So IPv6 has actually been around for quite some time. And if anybody had asked me when I first started teaching in the early 1990s whether IPv4 would still be around here in the mid-2020s, I would have said absolutely not. Guess what? I was wrong. So we are using IPv6, but certainly not everyone is, because as I've mentioned previously, there's so much legacy. You really it's not going to be easy to get rid of IPv4, but that doesn't mean that we shouldn't move ahead and take advantage of some of the self-configuration features, some of the security features, etc., that come with IP version 6. So let's take a look at what an IPv6 address would look like. Notice it's 128 bits. That's 4 times as many bits as we had with an IPv4 address. Okay. And now that doesn't mean there's just 4 times as many addresses, right? this is, remember, we're dealing with powers of 2. So I heard once that with IPv6, basically every square yard on Earth has something like 3,000 potential addresses that could be assigned to it. So we have a very, very large address space. Okay. And we have 8 hexadecimal sets of 4. Okay. And notice that's why we're not using, yeah, this would be a really long number if we were using binary notation. Okay. So that's why we're using hexadecimal notation. Um, and, since each hexadecimal number corresponds to 4 binary bits, then each of these blocks of 4 then is 4 times 4 or 16 bits. Now, yes, yeah, the number of addresses right here, 340 undecillion. Okay, and I don't know how much that is, but it's a lot, as you can see right here, addresses. Um, and of course, it's unrealistic to assign all these because we do need to split them up into subnets and multiple different users. But just to put in perspective that we're dealing with a very, very large number here of potential addresses in the IPv6 address space. Now, something that we can do in IPv6 that is not possible and frankly really not needed in IPv4 is we can actually simplify an IPv6 address. Okay, so notice we've got 2 groups here of all zeros. Okay, and what we can do is we can just use 2 colons, and everything between those 2 colons is assumed to be zeros. Now, that also means, since we're not quite sure where that ends and where that starts and how many zeros it would be, we can only use one set of double colons in any given IPv6 address. Okay, so an IP, again, a double colon can only exist once. Okay, now there are other things that we can do. For example, I hear these leading zeros. We can get rid of those. Um, we can get rid of this as well, but notice since we already used a double colon right here, we can't also get rid of this. We need to do something else here. Again, we can get rid of the leading zeros, but we have to leave at least 1 0. And again, we can delete the leading zeros really in any of these. And here it is. Okay. So yeah, so we can take this long address of 128 bits. Okay. And the address doesn't get any shorter, by the way, but we can simplify it by removing leading zeros, such as a 0 before the F56 right here, or the 3 zeros before the number 8, or the 3 zeros before the number 4, or the single 0 here before the number 2. Okay. Or again, the 2 blocks right here between these colons. Okay. Because since we know where the end is and we know where the beginning is, then we know what's missing right here. Okay. So again, but we can only use one set of double colons to shorten an IPv6 address. As we mentioned, we have the prefix, the first 64 bits, and then the interface ID. And if you go back to IPv4 terminology, the prefix is really the network address, and the interface ID is the host address. But hang on, Dr. G. So you can have that many hosts in a subnet. Yeah, since we have so many addresses, we can be rather generous in how those are assigned. Um, but yeah, we've got a lot of 2 to the 64th different possibilities, which is a lot. Okay. Now, um, speaking of network address, so the network address, which is in our prefix, we can split that up into the site or the location. Okay, that would be assigned by your ISP, and then we can create subnets within that. Okay, so this will be kind of like a subnet address. It's still part of the network ID as a whole, and um, for the prefix, but that's where we can then and again, 4 plus 4 plus 4 plus 4, we've got 16 bits, so 2 to the 16th, which is about roughly 65,536 different subnets if we were to use an entire group of 4 hexadecimal characters right here. And then we have the unique identifier. Um, and also known as a modified UI64 interface ID. And that is the last 64 bits or the last four groups of your IPv6 address. Okay. Um, and we have a MAC address right here. That's 48 bits. Okay. So we've got 6 pairs, so a total of 12. Okay. And then we have a binary number. Okay. That is my 64 bits right here. Okay. So we're generating a new hex number from the 7th bit right here. So we're basically including the MAC address in our network address, in our host address, okay, in our interface ID. And that MAC address, where does that come from? It comes from your network card. Okay, so we get truly unique addressing within IPv6. And yep, here's our modified interface ID right here. And yep, use your A and 8. Okay. All right. If we want to run both IPv6 and IPv4 on the same computers, then we need to install what's called a dual stack. So that's an IP stack that supports both IP version 4 and IP version 6 packets. And if we wanted to enable that IPv6 operation within an IPv4 fundamental network, then we can do that via a technique called tunneling, which places one packet inside another. And there's a couple different varieties. One is called the Teredo tunneling. Again, IPv6 packets inside IPv4, and each host does the encapsulation and decapsulation. And then we've got what's called 6-to-4 tunneling. Again, IPv6 packets inside an IPv4 packet across the network. And then we also have 4-to-6 tunneling, um, where the routers are actually doing the encapsulation and decapsulation. There is also what's called an intra-site automatic tunnel addressing protocol, or ISOTAP, and that allows for IPv6 network traffic to then be converted by the router into IPv4 traffic on the other side. So if you have a growing network, and part of it is running on the old protocol IPv4, and the other part is under IPv6, then you can still make that happen. Now, we haven't answered the question, what happened to IPv5, right? Why 4 and then 6? Well, 5 was a suggestion. It was tried, but then people didn't think it would meet the needs of where we needed to go with the internet. And that's why IP version 5 was just set aside and basically skipped in favor of IP version 6. And if IPv6 is anything like IPv4 when it comes to how long it lasts, we'll probably have it for many, many years. And the real big problem with IPv4 is really just that we don't have enough addresses anymore. So we needed a new address space. But also a lot of people would argue that with IP version 4, a lot of considerations, including security, were band-aids. So they were afterthoughts. And with IPv6, we've got things pretty well built in, a lot of new features that are making communication much more secure and much more efficient. Now, how do clients get IPv6 addresses? Because in IPv4, we talked about DHCP, we talked about manual configuration, right? Well, let's talk about some of the different IPv6 addresses that exist and how a client might be able to get access to one of those addresses. So first, we have what's called a link local IPv6 address. Okay, and that's a local address. It works on the local subnet, however big that may be. It allows you to talk to hosts on the same subnet, and it's not forwarded. And every client will always have one. So this is kind of like an automatic private address. I'm not calling it a piper because it's not. Okay, but there's a specific purpose for this local address, which is in fact used for automatic address configuration and also for figuring out who else is providing what services on the network. So that's what we call neighbor discovery. Okay, and that link local address starts with a hex value of FE. Okay, and the 10th bit must be a 0. And so here are some possible addresses right here. Okay, so again, the 1, 2, 3, 4 ones right here, that's your F. And then 1, 2, 3, and then 0, that's your E. Okay, and then a number that follows. So this would be 8, for example. Okay, and again, the 10th bit right here um, must be a 0. Okay, so here is the typical link local address, and this would be numbers that are assigned. Okay, um, and yeah, this this would be the IPv6 prefix. So basically, the prefix in this case would be the indicating the local network. Okay, and then we've got an interface ID here of 64 bits that would follow. Now, we also have what's called a unique local address, which is a private IP address in the sense that we know it from IPv4. Again, also stays on the local network. An FC00 with a /7 prefix, so that's 7 bits that we're using. And it either would start with an FC or with an FD, and it's followed by the global ID, so that is a unique private local address. And then we have a global unicast address, which again is a unique address. And yes, notice we're assigning multiple addresses to the same host here in many ways. Okay, and the ISP would issue the global routing prefix so they can connect to any other network, and the prefix starts with 2000. Okay, so that is for any device to communicate out across the internet. And then we have a multicast address where one device sends the same data to different clients. And here we're starting with FF00 /8, and then there's a local multicast as well. So all nodes on the local network, and all DHCP servers would be differently indicated as such. So there are different kinds of addresses in different parts of the world. But in this case, notice these are all very similar addresses. In fact, it's the same address for what's called an anycast. So what we're making happen here is that each one of these hosts that has that anycast address is part of this group of of clients that are receiving a message from a centralized location. So this could be used for streaming, for example. That's where you would assign anycast addresses. And then for testing, we also have a loopback address, and that is the 0001 at the end, or we can just use that double colon and the 1 for the last group right here for the 16, and that is your testing and troubleshooting address. If you want to make sure that your IP stack is properly working, that's when you would ping the loopback address for IPv6. Now, we didn't quite answer how these addresses, these various types of addresses, are actually given to the clients. We still have manual configuration or static assignment, just like we did with IPv4. That will be used for servers and other devices that you don't really want moving around the network. And then we have a static partial, where the prefix is manually assigned, And then the interface ID uses that EUI64 format based on the MAC address. Then we have what's called stateful auto configuration, and that uses an DHCP version 6 server to assign IP configuration. And then we have similarly a stateless rather than stateful auto configuration, which uses something called Slack. Okay, and Slack is stateless address auto configuration. Um, that's used for the IP address itself, and then the other information comes from the DHCP version 6 server. Okay, and here's the process for Slack. So we get a link local address. Um, then we use a process called DAD to check that that address is in fact unique. And then we send a recognized or accepted message to the multicast. And at the end, when the router and the client are part of that process done with their communication, then we've got a combined interface ID with a prefix to come up with an IP address that way. Okay, so much for IPv6. So here are the 5 different addresses that we talked about. Link local, unique local, multicast, anycast, and loopback. Here's how we assign those addresses manually or in conjunction with the UI 64. Then stateful auto configuration again would be using the DHCP version 6 server, and the Slack process for combining a prefix with the client or host ID. There's a lab, and you will be using IPv6, but you'll find, even though it sounds more complicated at the beginning, just because the addresses are longer, there's less configuration that you as an administrator have to do once it's all set up. And it's really relatively straightforward. The clients kind of find the addresses that they need for the different purposes. So if you look at an IPv6 configuration, you may well see different addresses, and that's intended, and that's normal. Okay, so check that out in lab 7.4.8. And then to finish up section 7.4 here, why is IPv6 needed? We needed more addresses. We needed more security. We needed more efficient transmission. The format is a total of 128 bits, or 16 times 4, so 16 hexadecimal groups. Actually, let me see, we have 16 times 8, so that's 8 groups, but 16 bits inside each one of them. Okay, so remember hexadecimal is 4 bits, so 1, 2, 3, 4 in each group. So that's where your 16 and then 8 groups times 8, that's your 128 right there. How can you simplify an IPv6 address? You can shorten it by eliminating leading zeros. And if you have groups of zeros, then you can actually use that double colon. Remember, you can only use that once. The 2 parts of the address are your prefix and your client ID. And then you can use tunneling to either Teredo or 624 or 4 to 6 to allow IPv6 hosts to communicate over an IPv4 network. And difference between stateful and stateless is how the client ID is generated with your for your IPv6 address. Whoa. Okay. This is new for most of us, but that's okay. We'll learn more about it as we go. And again, you're going to be dealing with IPv6 if you haven't already in many of your other classes. So much for section 7.4. We'll start talking about wireless networking. So we're going to go down a few layers here in our OSI model, and we'll do that in the next section, which is 7.5.